Hi everyone, I'm Gauri from Carnegie Mellon University, and today I'm going to talk about Overlap-Local-SGD, which is an algorithmic approach to hide communication delays in distributed SGD. This is joint work with Jianyu Wang, who is my PhD student, and Liang, who is a master's student at CMU. Now, since this work is about distributed SGD, let me start off by giving you a brief background about stochastic gradient descent in the context of machine learning. Many of you might already know that SGD is the dominant algorithm used to train neural networks because the backpropagation algorithm is a special case of SGD. At its core, SGD is an iterative method to optimize an objective function. In the context of machine learning, the objective function is the empirical risk function, which is the average of the losses incurred at the different points in the training dataset. And SGD optimizes the parameter vector x by taking the current value of x and moving along the direction of steepest descent by computing the gradient g, which here denotes the mini batch gradient. That is, it's the average of the gradients at a batch of b data points which are sampled from the training dataset. So using this mini batch gradient, SGD updates the current version of the model parameters to obtain xk plus 1, and then this procedure repeats sequentially. So since SGD is an inherently sequential algorithm, if we just apply it naively to the enormous training data sets and the large models that we have today, training on a single machine can take several days or even weeks. So because of this, it is imperative to distribute SGD across multiple machines so that it can finish training a model in a reasonable amount of time. And a common way to distribute SGD is what is called fully synchronous SGD. This means that if you have a system of M workers, in this example we have 4 workers, then the data is partitioned across these 4 workers, and in every iteration, a worker takes a mini batch of samples from its own local dataset and performs one local step of SGD, which is shown by the equation here. So after each worker performs one local step, we use either a central parameter server or an all-reduce aggregation mechanism to aggregate all the models that are trained by the different workers. So after this aggregation step, the model at the ith worker will just become an average of all the workers' models. So all the workers achieve consensus whenever we do this communication step. And after communication, the process just repeats. Again, all the workers do one local update and then communicate and so on. So this is the vanilla fully synchronous SGD mechanism. As you might predict already, a problem with this procedure is that the communication step could take a really long time depending upon the system that we are using. So if you have a bandwidth limited or high latency network, which is very common in the context of federated learning where the workers are mobile devices, this communication delay can even dominate the computation time that the workers take to perform the local SGD steps. So because of this, and because of the federated learning motivation in recent years, there has been a lot of interest in coming up with ways to reduce this communication overhead. And one of the ways to reduce the communication delay is to perform local SGD. That is, each worker, instead of doing just one SGD step, does multiple local steps of SGD and then averages with the other workers. So as a result, because we are reducing the frequency of communication, the communication delay gets amortized across the number of steps that each worker is taking locally. This is one way of reducing communication. Another orthogonal way is to reduce the size of the transferred message. So instead of reducing the frequency of communication, each worker can quantize or compress the gradients or model updates that they are sending over the network. This can be achieved by different methods. Some examples are power SGD, sign SGD, etc. And this is another way of reducing the communication overhead. And these two complementary ways can actually be combined to do local update, quantize SGD. However, in this work, we are going to explore a third and relatively unexplored way to reduce communication delay. And that is that we take local SGD as a baseline and come up with ways to hide the communication delay. What do I mean by hide here? I mean that we come up with ways in which we can overlap the local computation and the communication so that workers can continue doing local updates without waiting for this communication or model aggregation step to finish. And Overlap-Local-SGD, which I'm going to explain in the next few slides, is a method that achieves this. Overlap-Local-SGD has convergence guarantees and it is validated by experimental results, which I will show as we go through the rest of the talk. So what is Overlap-Local-SGD and how does it achieve this simultaneous communication and computation? Let's look at the steps. We start off by initializing each worker with a model version, which is denoted by xi. So this is just a copy of the model that is stored at the ith worker. And in addition to this model version, each worker also stores z, which is an anchor model. This anchor model is common across all the workers and is stored at each worker. Now, given these two model versions, in the first step of Overlap-Local-SGD, workers independently perform local SGD steps. So these can be tau local steps of SGD performed using their own partitions of the dataset. And after doing these local steps, in step 2, workers average their local model with the anchor model. And by averaging, what we mean is that the local updated model, xi, is pulled back towards the anchor, and the amount by which it is pulled back is controlled by this parameter alpha. Note that this step does not require any communication between the workers because the anchor model z is already stored at the workers. So this is how we do the local computation at each worker. Now, the next step aggregates and averages these anchor models across the workers. So while that is being done, while we are averaging x plus, which are the updated models at the different workers, a different thread performs local computation at the workers. So what the workers do is that after doing these local steps and then averaging with the anchor model, they proceed with the next set of tau local updates without waiting for this communication to happen. And the communication goes on in a parallel thread, and it just simply averages these updated models in order to update the anchor, which is stored at different workers. So let's look at this in the execution pipeline picture to understand how exactly local update SGD is reducing the communication delay. In particular, it reduces delays in two different ways. Firstly, observe that each worker only needs the anchor model from tau iterations ago, because it's going to do tau local iterations and then pull back its model to the previous anchor. So because of this, the anchor can be updated while a worker is doing the next round of local updates. And we observe that in this picture, each worker can do its local updates and pull back its model towards its anchor. That pullback is shown in blue. And while it is doing the next round of local updates, the communication, which averages these anchors, can happen in parallel. So this is one method of reducing delay. Another bonus benefit of Overlap-SGD is that it intrinsically provides some robustness to straggling nodes. And this is because some workers can do local computation faster than others, and the slow workers can be up to tau iterations behind a fast worker. So in this example, if device 2 takes a longer time to finish its local computation, device 1 does not have to wait for it. It can proceed to the next round of updates, and only if device 2 is more than tau steps behind, then device 1 has to wait to get the updated anchor in order to go ahead with the next round of updates. So in this way, local update SGD reduces communication delay and also mitigates stragglers. Now let's see what happens to the convergence. We are definitely reducing delays, but are we losing something in terms of the error convergence? This result shows that the error in the averaged model, YK, which is the average of the local models and the anchor, is bounded by this quantity. And some observations here are that there exists a best value of alpha. The alpha is the pullback parameter. So if we choose the appropriate value of alpha, we'll get the tightest possible bound and subsequently a fast convergence. Another observation is that only the higher order terms of this expression depend on the number of local steps and the communication methods. So as the number of iterations k becomes sufficiently large, the convergence rate is dominated by the first term, which in fact matches fully synchronous SGD. So what this tells us is that asymptotically, local update SGD with overlap will perform as good as fully synchronous SGD. Now let's look at some experimental results. These are conducted on a cluster of 16 machines in CMU, and the data set is CFAR10. The network that we are training is ResNet. The left-hand side plot shows the test accuracy versus the additional synchronization time per epoch. What do I mean by additional synchronization time? This is the total time spent on one epoch minus the local computation time, which is same for all the algorithms that we are comparing here. Only the communication time is different. So here we are comparing Overlap-Local-SGD with local SGD and power SGD. Power SGD is a quantization method. And the cross here, which is one extreme of local SGD, is fully synchronous SGD. As you can see, Overlap-Local-SGD uses very little additional synchronization time per epoch and still achieves high test accuracy. The training curves on the right-hand side also confirm this insight. Next, let's compare this with some other overlap SGD algorithms. There are actually very few methods that propose this way of overlapping communication and computation. One of them is COCO-DSGD, which is a very recent work. It uses a similar idea, but a slightly different way of updating the anchor model. Elastic averaging SGD, which was proposed in 2015, is also a slightly different method. And elastic averaging actually did not note that you can overlap computation and communication and did not implement it in this overlapping fashion. So we compared the proposed method with these two and observed that this new algorithm empirically does about the same or slightly better than these existing methods. And the learning curves also validate that insight. So summarizing, In this work, we proposed Overlap-Local-SGD, which is a method to simultaneously perform local computation at the workers and communication between nodes. And as a result, it provides robustness to stragglers and reduces the communication time per iteration. And it does this while providing strong convergence guarantees that hold for non-convex loss functions and also hold for non-IID data partitions across the different nodes. And we validated the performance of this method on deep neural network models and showed that it actually works in practice. So that's it. Thank you for your attention and for attending my virtual talk. The code of Overlap-Local-SGD is available at this link if you're interested in looking at the code and running it by yourself. Thank you.